So this is a slightly longish chapter with lots of hypotheses, really not so much as theories, because the data is good enough to suggest many things, but none of them can be totally confirmed. What do we mean? We are looking at the unstable ice age carbon cycle, and we already discussed this while we looked at this figure already several times. We are looking at time going back here, which is typically what paleoclimate people do. So this is age in years before present, so 50,000, about 600,000 years here from the Vostok ice core from Antarctica. We talked about, and this is the depth of the ice core up here in meters. So we're looking at CO2 in parts per million by volume, methane parts per billion by volume, which most of you probably know, and the insolation forcing and the temperature scale and the delta O18 scale are on this side. We talked about how building a glacier while the temperatures are cooling is a slower process, because as the temperatures, global mean temperatures, get colder, the atmosphere holds less moisture, which means the snowfall rate at high latitudes where the glaciers are building will keep slowing down. So that takes a while, and then the melting phase goes very abruptly. Right? We talked about Milankovitch cycles, which explain the initiation of the glaciation or the retreat of the glaciers, deglaciation. And the key question about the unstable ice age carbon cycle really is to see that the carbon cycle in at this time scale is actually a positive feedback. So if you look at the cooling phase because of the radiation forcing, you can see that that's not always so clear, right? So this is insolation at 65 north, and we are looking here at the deep ocean delta O18, which corresponds to buildup of glaciers and melting of glaciers with the fractionation of the oxygen during evaporation and precipitation, as you remember. So the buildup and drawdown of CO2 goes in the positive feedback direction. While cooling, if you draw down CO2, you're going to reduce the greenhouse effect, and you're going to make the temperatures even colder. This is as opposed to the geologic time scales we looked at, where the warmer temperatures, more humidity, more rainfall led to faster weathering rates and drawdown of CO2 as a negative feedback, right? So the idea here is to go into some details and look at few ideas that have been around to explain what are the processes behind the drawdown of the CO2 by about 80 to 100 ppm from deglacial stage here at about, let's say, 300 ppm, and the peak of the glaciation at about 200 or less in ppm. So we have to explain a change of 80 to 100 ppm in CO2 increase and decrease between deglacial and glacial stages. Okay, there is a corresponding methane change as well. And many people would simply argue that they are not related to each other, that glaciers simply cover the land by putting glaciers on top of vegetation, and that could explain the drawdown. But actually it turns out that when you look at the carbon isotopes, other sediment data, ice core data, biological evidences, and so on, delta C13, etc., it's clear that it's the ocean that's playing a major role in this drawdown and release of CO2 from glaciation to deglaciation. So all the hypotheses focus around that. The first thing to explain, of course, is also the phase lead lag between temperature and carbon dioxide. We have already mentioned that the temperature here leads by let's say 10 to 30,000 years it leads carbon dioxide changes. Why? Because the radiation forcing at 65 north, you remember 65 north is critical because that's kind of the latitude which can determine how much of the snow from one season melts by the end of the summer season in the northern hemisphere. If it's not melted by then, as fall and winter set in, it's going to stay, and then more snow is going to fall on top, so you're going to accumulate snowfall. Of course, there are details that even if the temperatures are warmer than 0, the snowfall rate can be so high that the snow doesn't always melt. But let's leave that detail for now. Okay, so that's the idea, that the orbital forcing is leading the warming, the beginning of the warming, so temperature leads, and then the glacier melt or build up changes the albedo, and then feeds back positively, and then we have the response in the ocean and on land a little bit because of the vegetation changes, the buildup or drawdown of CO2. So that phase lag is easily explained, as well as the phase lag here. We are increasing CO2 now by fossil fuel burning, and increasing methane as well by land use activities, rice paddies, cattle, etc., etc. And you can see that those rates of increases are much faster than anything we have seen in a long time. But the temperature change is not that fast, basically because the increased greenhouse gas emissions are changing the radiation budget, and the excess energy, 93% of it is going into the ocean, so it doesn't show up in the atmospheric temperature. A lot of the energy goes in evaporating, in melting glaciers, and so on. So the temperature increase is not going to follow the rate of increase of CO2, but if the system is true to its inherent properties, then you know that even if you stop emitting greenhouse gases, this warming will continue, which is what we call committed warming. Okay, so those are kind of the basics. This is another figure that's showing Skeptical Science is a good site, in case you don't know, where it discusses random doubts raised by often vested interest deniers, but sometimes skeptical people who want to learn as well. So we are looking here at Antarctic composites of CO2 and proxy for global temperature. As again, temperature leads, and here you can identify the last glacial maximum where the CO2 and temperature had reached the same phase, down at about 180 to 183 ppm, reaching up to 280 or so by 1750. So last glacial maximum, this is the older, driest, this is the Bowling Alarod. These are temperature signals in the Antarctic, which are local warmings and coolings that happened at relatively rapid rates. And the younger Dryas is here, and the Holocene, where the temperatures have remained fairly flat when the modern human being evolved. So all the questions are about how well can we handle if we start to perturb the carbon cycle and increase the temperatures at a very rapid rate. Many species go extinct when temperatures increase at a very rapid rate because they cannot adjust or adapt, but many do survive. Many have survived past warmings and coolings. Okay, so that's the main question here. There are additional time scales as well. This is from the Greenland ice core Delta O18, looking at the modern interval, and then going back to about 80,000 years before present. The extent of the ice sheets on the continents are seen here, and the corresponding sea level changes. So when glaciers build up, sea level drops because you're moving water from the ocean onto land and locking it up. The main point here is that there are some very abrupt changes called the Dansgaard-Oeschger events, which happen on what are called millennial timescales, so anywhere from 1500 to 2000 or 3000 years or so. And there is plenty of evidence that these warmer and colder events have happened throughout this period, but we don't have a very good explanation as to what exactly drives these timescales. So the other faster timescale I'll mention here is the so-called Younger Dryas, which happened while coming out of the last glacial maximum. Melting was happening, temperature was increasing. This is from Dome Sea in Antarctica, Cariaco Basin, Greenland ice cores, and so on. And then something happened, and suddenly there was a drop in temperature and cooling. It's called Younger Dryas and Older Dryas, basically because these cold temperature flowers in the Arctic Circle appeared and disappeared. They appear when the glacier melts, warming happens, and they disappear again when the refreezing happens. The best idea we have is related to the Atlantic meridional overturning circulation, which I will come back to in the context of explaining these rapid changes and some other changes like these millennial timescales. So that's the idea of a unstable ice age carbon cycle. So we'll run through several ideas of what could explain these, but the main message is that none of the hypotheses can explain the 100 ppm or so change, 80 to 100 let's say, but it's pretty clear that it's the ocean that somehow played a key role in drawing down carbon and re-releasing it from ice age to the deglacials or interglacials. Okay.